Welcome back. In the last two classes, we started discussing about two-dimensional and multi-dimensional NMR, in particular two-dimensional NMR, where I discussed the limitations of one-dimensional NMR spectra, the need for going to higher dimensions, and I also discussed about the dimensionality time constraints, the size of the molecule which can be studied by different types of multi-dimensional NMR experiments, and varieties of things we discussed. A lot of information was given to you. And now we have to appropriately choose the particular dimension. Experiment, particular dimension. The dimensionality choosing is very important for your molecule. Now, how do you choose the dimensionality required for your molecule? Okay, we will go for that. How do you require to choose the dimensionality? See, that is very appropriate. You cannot take a simple molecule, like for example, a molecule of this size, which is having 1, 2, 3, 4, 5 different types of protons present. And then you just can't say just because the molecule is available and the spectrometer is available for me, I will go and do the 800 megahertz spectrum. I will record 800 megahertz spectrum. And I will record two-dimensional. I will record 3D NMR. What is the need for that? We should understand what you have to go to higher dimensions only when the lower dimension cannot give you the required information. It depends upon size of the molecule, number of chemical inequivalent protons. For example, if a molecule may be big, it may have a number of protons which are chemically equivalent. For example, you take kekulene, or for example, you take aniline. See, a lot of protons are there, but many of them are equivalent. In which case, you may have only 1 or 2 types of chemical inequivalent protons. So, then what is the point in going to higher dimensions? So, higher dimensions choosing is very important. You have to first look at the type of spectrum you get in the 1D NMR, and afterwards see whether you can extract the information in a straightforward manner with a easy analysis. Then you have to choose the appropriate dimension. Okay, let us look at a molecule like this. You take a 1D NMR. It is a very simple spectrum. You have only well-resolved peaks and well-resolved multi-state pattern, multi-state pattern. Very easily you can analyze. This will be a triplet because of this, a quartet because of this. Looking at it, hardly it takes maximum 2 minutes to analyze the spectrum. Worst come to that, you might, if you want to analyze and measure the separations and get the chemical sheet along with the coupling information, it won't require more than 5 minutes for you. So 5 minutes for recording the spectrum if you take. In 10 minutes, this molecule can be completely analyzed, taking the 1D NMR spectrum. Then the question is, why do you require 2D for this? Why do you require higher dimension? For this molecule, there is no need of two-dimensional higher dimensions. Only one dimension, simple one-dimensional proton spectrum is sufficient. If you want to get the carbon coupling, carbon information also, one-dimensional carbon will do. Simply, you see, using a depth, you can identify the carbons attached to different protons, everything. Very simple. It will not take more than 5 to 10 minutes for the analysis. So you can safely discard higher dimension requirement for molecule of this size. Now let us go to a molecule of this size. It is strychnine. This has large number of protons, like as you can see, number of protons chemically inequivalent have been marked here. Take a proton spectrum of this molecule, one dimensional. In a reasonably high spectrometer frequency, maybe 600 or 500 or 600, you get a very beautiful spectrum. You see, it's a fantastic spectrum, well resolved, very easily you can make the assignment. I tell you, even for this strychnine molecule, you don't require more than one dimension. Frankly, here you took let's say 5 minutes to analyze. Here you may take 15 minutes or half an hour to analyze. Okay, take 1 or 2 hours if you want to completely assign and extract the coupling information. Everything if you do, it will not take more than 2 to 3 hours maximum. complete analysis, including the recording of the spectrum, will not take more than 2 hours or 3 hours. Complete analysis. Even then, you don't require 2D and higher dimension. But okay, to save the time, to make our analysis faster and easier, we can go for the 2D for this. Reasonably acceptable because reasonably good size of the molecule, you can go for 2D. Where you see well resolved peaks are there, you can try to understand everything. It's okay, reasonably good molecule, reasonably medium size molecule for which you can go to 2D. But you don't require 3D and higher dimensions for this molecule. You should not go to 3D and higher dimension. What do you get out of that? Of course, even for small molecules, sometimes you go to different type of experiment depending on the particular information which you want to derive. For that, you can design an experiment of your own. You can go to 2-dimension, 3-dimension, etc. But for the routine analysis, 2-dimensional experiment is more than sufficient even for the strychnine molecule. You don't require higher dimensions. Then the question is, when do I require higher dimensions? This is where you have to go. Take for example, carbon 13 and nitrogen 15 labeled, uniformly labeled ubiquitin is reasonably big molecule. I don't know, maybe it has more than 50 amino acids. And each amino acid you can consider as a particular coupled spin system. All protons, right from NH proton to methyl, if you go, there are so many protons in between, many of them are coupled among themselves. As a consequence, the spectrum is really complex. I understand. Even 1D or even 2D is little difficult to analyze spectrum of molecule of this size. Okay, so you have to resort to 3 dimensions. This is a typical spectra of an experiment called 3D HNCO of this ubiquitin molecule. Just to show you how the 3D spectra are represented. Okay, here 3 dimension means in 1 dimension we have a proton channel, other dimension we have nitrogen, in 3rd dimension we have carbon 13. In 3 dimension, 3 different nuclei can be chosen. And you have analysis of the 3D spectrum is not pretty straightforward like 2D. You have to take planes in different directions. You can take a plane along this axis, you can take a plane, you can take a plane like this, or you can take a plane like this, or you can take a plane like this. And then accordingly, you can break this 3D spectrum into several 2D spectra and then make the analysis. Okay, this is not fairly a difficult job. It can be done. But what I want to say is, for a molecule of this size, you definitely require higher dimension. This is how you have to choose. Now, what is the benefits of higher dimension? One thing, of course, you saw here, analysis becomes simpler. Why? We'll see that. Let us consider a simple example. We have a molecule where we have different chemical shifts. Let us say it could be homonuclear. There are several chemical inequivalent protons are there. We have several chemical shifts. It could be heteronuclear, doesn't matter. Or we have couplings. Each proton is coupled to other proton or other NMR active nuclei. You have a number of couplings present. In each case, if I take a 1D spectrum, let us say proton coupling, proton carbon couplings, everything are overlapped like this. All peaks are there. We have couplings, we have different chemical shifts, everything, which are identified by different colors and different sizes. The small circular spherical balls represent couplings. Bigger spherical balls here, what is given, represent different chemical shifts. It could be homonuclear. Now, it could be heteronuclear, but I have taken, let us say, a homonuclear case, no problem. Doesn't matter. I don't have to specify the type of 2D experiment. I have taken a 2D experiment, something which I know I can resolve this. What I am going to do is, first, I can separate out all the couplings in 1 dimension on the basis of the size. So all smaller coupling values, the smaller balls, smaller size spherical balls are pulled out in this dimension. Now, the complexity coming because of this is reduced quite a bit already. You have some of the peaks shifted up in 1 dimension. Now, I can do one more thing. Why not is shift Why not I separate out different colors of the balls? Here I can put black color in this direction and red colors in this direction. At the same time, I can pull out the different sizes of the small balls, if small ball size in this dimension. Now I took 3 dimensions, and three informations have been put in 3 different dimensions. What did you do? By doing this, you have reduced spectral complexity. The dispersion became much better. Higher spectral dispersion came instead of so many peaks congested in a small area where it was clumsy for us to analyze. Now you have simplified the complexity. So because of this spread of the peaks, you have got better and better dispersion. Your analysis becomes much better. You understand the benefits of higher dimension. First and foremost, you can simplify, spread the information content in different dimensions where you can extract the information the way you want. You can orchestrate the experiment, design the experiment in an orchestrated way to extract the coupling information or chemical shift information or any respective information of your choice. Okay? This is the biggest benefit of higher dimensions. Okay, you understand now. I have already told you how we have to choose the dimensionality and what higher dimensions will benefit you. Okay. Now the question is, I said you go to higher dimension, but I did not tell you which type of experiment you have to choose. You may ask me a question, I have a reasonably medium size molecule, molecular weight of 500 Dalton or 1000 like that. Now I don't know what experiment I have to choose. I know the spectrum is complex like strychnine, which I showed you. But you may say, it's slightly complex than strychnine, but I have to analyze the spectrum. Tell me what experiment I have to choose. That is another thing. Choosing the proper experiment is very important in deriving the information. So, now I am going to tell you what are the types of 2D experiments which can give you information. What type of information you can get from that. Basically, I will classify the 2D experiments or in general multi-dimensional experiments. You can take it as multi-dimensional experiment, but my focus is on 2D today, and for the rest of the remaining 1 or 2 classes, I focus on 2 dimensions. So we say it is 2D, but in general, you can classify these for any multi-dimensional experiment like this. Okay, the broad classification of 2D experiments are like this. One is correlation type experiments, where information in 2 dimensions are correlated. What type of informations are correlated? It can be chemical shifts of homonuclei. For example, I have a molecule, reasonably big molecule which I showed you recently. 5 different chemically inequivalent protons are there. Not big, okay, S molecule with different types of chemically inequivalent protons are present. Now, when I wanted to analyze the spectrum, what I was looking for? Coupling pattern, so that I know which is the coupled neighbor for each proton. I had a CH3 group, attached to it there was a CH2 group. I know CH2 will split CH3 into a triplet. I also know CH3 will split CH2 into a quadrat. Based on that, I could say this is CH3 attached to CH2. Similarly, for other protons, I can do. You understand? Now I want to see the carbon assignment. I go to carbon and take the carbon coupled spectra or depth spectra and identify different carbons. So reasonably with 1 or 2 small tricks, I can make the assignment of that. But if I give you a big molecule like we saw in the protein, so many amino acids are present, so many different types of protons are present. Now in a crowded spectrum, I want to know which proton is coupled to which peak, which is the peak corresponding to this. Let us say I have a bunch of peaks here with this proton may be experiencing coupling with different types of other nuclei surrounding it or coupled to it through covalent bond. Now, how do I know what is the coupling strength, which is coupled to which is this immediate coupled partner, which is this coupled one for 2 bonds away. Which proton is coupled 3 bonds away? I have to do the experiment. For this, in the olden days, we used to do a typical experiment called decoupling, which in the decoupling I already told you, heteronuclear decoupling. Same way we were doing homonuclear decoupling, that also I explained. If I have a coupled spin system like this, so what I have to do is, I will irradiate at this frequency and see how the proton is, how the multiplicity here is getting changed. If it becomes a singlet, I know this is coupled to this. Let us say it was a quartet or 4-line pattern. Now it becomes a 2-line pattern because of this. Then I say this is coupled to this, and this doublet is coming because of another proton which is coupled to this. So like this, I have to do n number of experiments called selective decoupling experiments to identify the coupled partners, so that sequentially I can go CH3 is coupled to CH2, this CH2 is coupled to this CH2 is coupled to next another one, like that. Finally, after doing number of such experiments, I know the complete molecular structure of conformation, and I'll get the functional groups present, how they are present in the molecule. CH3, CH2, CHOH, which is there. I can start writing the structure. For molecule you like ubiquitin or some other big protein molecule, how do you do? It is not as simple as I said for a small molecule now. For that, we have a correlation type experiment which is simple, where I can correlate the chemical sheet of one proton which is coupled to it in another dimension. I have a 2-dimensional spectrum. In this dimension, let us say I have a proton here which is coupled to another proton. This information, coupling information, I'll spread in 2 dimensions. I know if there's a peak here, this is coupled to this. So this type of coupling information, where the 2 protons are scalar coupled, mediated covalent bond, can be correlated. We can correlate 2 protons which are coupled to each other, or more, including long range coupling. If one proton is experiencing many coupling, all of them can be understood which is coupled to which. Sequentially, we can start going one by one and make the assignment. That is called chemical shift correlation. We can correlate chemical shifts of homonuclear spins which are coupled between or coupled among themselves. There are many protons. Same thing can be done in this experiment called TOXI, where whole spin system can be identified. And this is homonuclear. Of course, we can do another type of experiment called resolve type experiment. In the sense, when I looked at the complexity of the spectrum, I said we have chemical shifts. In addition to that, multiplicity is there because of J coupling. This multiplicity comes because of this one proton coupled to many other protons which are bonded to it, which has interactions with the neighbors. As a consequence, this one proton splits into multiplicity. So many multiplets are there. It could be doublet, triplet, quartet after all those multiplicity patterns which I discussed could be there. Now, how do you extract the coupling? Will I not simplify my analysis? If I pull out the coupling information in one dimension and retain only chemical shift in another dimension. Remember, these 2 parameters are invariably present in your spectrum. They come as a pair. You cannot avoid that. But is there any way I can resolve it? This is called separation type experiment. Here I correlate one information with respect to another through covalent bond, chemical shift to chemical shift correlation. Here I can resolve them. I can separate out the 2 parameters. I can get chemical shift in this dimension and pull out the J coupling in this dimension. Then what happened? I have greatly simplified the spectrum. These are called resolve type experiment. Simple example is called J resolve, where I can retain proton chemical shifts here. I can get only J couplings here. I separate out 2 information in 2 dimensions. So this is another class of experiments called resolve type experiment. Okay. Now the question is, you may ask me, what happens if I have multinucleates, several NMR active nuclei present in the molecule? Should I have to restrict this only to homonuclear case? Can I do heteronuclear experiment like correlation and resolution? Resolve experiment of homonuclear and heteronuclear, can it be done? Sure. Both type of experiments can be done for homonuclear spins and also for heteronuclear spins. Very simple. For example, homonuclear correlation experiments like this, Cauchy-Taxi, homonuclear result experiment like J-result. Similarly, heteronuclear experiment like HETCAR, heteronuclear correlation, HSQC, HMBC, heteronuclear J-result. Several such examples. As we go ahead, we'll understand some of the sequences. Of course, each and every sequence you can understand how we get the information. This can mathematically you can understand the spin physics, trace the magnetization pathway, how it is moving right from before application of the first pulse when it is in thermal equilibrium till the end. We detect the signal, how the magnetization is, what is happening to the magnetization, what is happening to the spins we can monitor. This is what all about designing of the pulse sequences and designing of this experiment. This is what is called manipulation of spin dynamics. We can do that to get the different experiment. Let us not go into understand the spin physics of each of these pulse sequences. That itself is a big semester course by itself. So since this is basically focused on application and utility in chemistry, we'll give one of the pulse sequence. I'll tell you how it works, or in a simple way without going deeper into the mathematics, because I don't want to frighten you. And we'll see how we get the information. And then similarly, we take couple of examples of varieties of the spectra and then try to analyze and see what we can get. This is what we are going to do today. The question what you can ask me is, okay, I know I have a molecule, I know the size of the molecule, and I know what type of 2D, what dimension of NMR experiment I require to do. And now what I said from the previous slide, you also know what type of 2D experiment you want to do. But what are the other information that I can get from 2D spectra, which we may not know? See, in the correlation experiment, you correlate chemical shape. J-result experiment, you resolve two parameters, separate out in 2 dimensions. But can we get any other information from 2D spectra which we can utilize later? Of course, there are number of informations available and you can extract from the 2D spectra. One, you can extract the coupling pathways, pathway of the two spins which they are coupled. You can extract the coupling constants by a result type experiment. You can get the coupling homo or heteronuclear in this dimension, chemical shift in this dimension. You can get long range couplings. That is very interesting. Let us say I have 1, 2, 3, 4, 5 or 6 protons are coupled. This proton has a long range coupling to this, which are 3 bonds away. This is 1 bond, this is 2 bond, this is separated by 3 bonds. Let us say this proton is coupled to this. Doesn't matter homo or heteronuclear. I'm looking for, let us say, heteronuclear case. Long range homonuclear couplings is very, very small. Doesn't matter. So for heteronuclear case, I will consider this is a carbon, this is coupled to proton here, 3 bonds away. Can I get this coupling? Only this coupling, suppressing these two. It is possible. You can get only this, or you can get only 1 bond coupling also. Like that, you can design experiment to get a specific information. You can get only long range couplings, or you can get only 1 bond couplings like that. You can get information on reduced dipolar couplings. This is another information which you get when you partially align the molecule. I said in the very first class, remember I said in the NMR can be studied in solid state, solution state, liquid state, and also I mentioned liquid crystalline phase, where you can partially align the molecule, where partially average dipolar coupling, chemical anisotropy, etc. will get reflected in the spectrum. That's what I said. So these are all called reduced dipolar couplings, called RDCs, which are extremely useful in getting the structure of biomolecule. Many times in biological application, biomolecular structure case studies, these RDCs are used as constraints. We get this value to get the geometry information. That is also possible. We can get NOE. What is NOE? We discussed nuclear over-hazard effect. So we can get to spatial proximity information. That is possible. We can get diffusion information. If you have a combinatory mixture of different molecules, they all will be diffusing at different rates. I can find out the diffusion coefficients of these molecules and identify number of components present in the mixture. That's a fantastic application. That is, I can obtain. If I go to solid state, we can get chemical sheet anisotropy, we can get dipolar couplings. Remember, these information are not obtainable from the solution state spectra. You know why? I already told you. Because the motional averaging, these information get completely nullified. You will not get it in the solution state. However, they are present in the solid state. We can get this type of information when I do solid state NMR. That's also this dipolar coupling. Again, further we can get homonuclear dipolar coupling only. We can get only heteronuclear dipolar couplings. That's also possible. So you understand, this is only a tip of an iceberg I am giving you. Okay, you can get lot more information from varieties of two-dimensional spectra. That is possible. Or if you go to higher dimension, you get much more information. So I would say there is a plethora of information we can extract from varieties of 2D spectra. Okay, and these are the typical 2D experiments commonly employed. If you go to the literature, let me tell you, at present, you can get several hundreds of 2D and 3D NMR experiments possible. Several hundreds. People have, many pioneers in this area of NMR spectroscopy who have been working, who have been doing research in this area. They have designed number of experiments. It is very much useful for us. We should thank them for contributing so much. Now there are a number of such experiments available. Just go to the literature and see any books on NMR. At least several hundreds. I can right now say about several 200 to 300 type of experiments available, or even more are available, more than several hundreds. So, but commonly employed some of these things in the day-to-day analysis. Of course, you can use correlated spectroscopy called COSY, where we can correlate one information with other information like chemical shift, homo heteronuclear. We can do spin echo correlation. NOSI, nuclear over-Raster effect we can do to get the spatial proximity information. ROSI, the same NOSI information we can obtain in the rotating frame, while rotating frame over-Raster effect. We can use double quantum filtered COSY. This COSY has certain limitations. When I do the COSY experiment, all these things are improvements. Somebody gives you develop a pulse sequence, one of the pioneer in the area develops one pulse sequence for some information, and then some other people who are working in the area will keep improving it day by day. So if there are certain constraints, if there are limitations, there are some issues related to one type of experiment, the improved versions will be made available later. Exactly. This COSY has some limitations. Now, as a consequence, DQF COSY came. This can solve, partially address many of the issues which were there in the COSY experiment, like that. Similarly, HSQC is an experiment where you can correlate chemical shift between two heteronuclei, like proton carbon or proton nitrogen, etc. And this is done in a different way. This is done in an indirect way, but what is called inverse detection. We don't directly observe carbon. I'll tell you when you go ahead. This is with using using what is called polarization transfer technique, which I told you in one of the classes, so that we can enhance the signal intensity. The same thing you can do for heteronuclear multiple bond correlation, in not direct one bond, like what we said, long range coupling. We can say this carbon is coupled to protons 2 bonds away, 3 bonds away. Directly I can extract that. I can get diffusion properties by DOSI experiment. Many of them I can simplify the experiment by using gradients instead of phase cycling. I did not explain much about phase cycling and gradients. Don't worry, that is not immediate necessity now. But just I wanted to tell you, number of hundreds and hundreds of such experiments are available for routine use. But the proper choice of what you want to do, you can get. You understand? Now, how do you design a pulse sequence? Is the next question. Okay, there are many of things, many pulse sequences there. Many information is available. I know what experiment to choose, but I know what information generally different types of experiments will give. But my question now is, how do you design different type of experiment? Of course, for this course, that is not a necessary thing. It is not the basis of this course. In this course, I am trying to tell you more from the application side of view, utility point of view. So there is no need to worry about it. But just to give you a broad idea, how the pulse sequences are designed. These pulse sequences are combination of various pulses with delays. Simple example, you take COSY. COSY has two pulse sequences, a 90-degree pulse, T1 period which is systematically varied, and then another 90-degree pulse, and start collecting the signal. So you have a T1, you have a 90-degree pulse, T1 period, another 90-degree pulse, and then start collecting the signal. And this is systematically varied. This is T1 and this is T2. Now this is a delay. So this is a 90-degree pulse. It need not be 90. It can be different angle in some experiment. Take for example, simple depth experiment. One of the last pulse was of different angle. We knew we can do depth 45, depth 90, depth 135. Accordingly, we got different information. Is it not? Similarly, it depends upon the type of pulses and the pulse whether you apply in proton or carbon, and what is the delay you are going to give. Remember, delay is very important. In depth and inert experiment, we found out after the magnetization was brought back to certain, there was antiphase magnetization. We knew if we start doing the decoupling, it will get nullified. So we gave a delay and made sure these components further evolve, and then afterwards we started doing decoupling. See, that small 1/3 of J delay was very useful there. Similarly, these pulses, the degree of pulses you apply, whether it's 90-degree, 180-degree, or 45, whatever the flip angle, the angle through which you shift the magnetization, tilt the magnetization, is called flip angle. The flip angle of the pulse and delay matters a lot. That will tell you more about your pulse sequences. Okay, and we can design based on what happened to magnetization at different delays and different pulses, like we saw by the vector diagram for INAPT and APT. Of course, every pulse sequence we cannot do by vector diagram. There is a way to understand by mathematics called product operators. That is a big chapter by itself. That is not the part of this course, so I will not tell about these things. We will see in one of the classes if we give next time. Next course we can discuss that. So, and then how do you have a specific delay, choosing everything we can do. Delay can be chosen based on the J coupling. Supposing J coupling is 10 hertz. J coupling is in hertz. Time is inverse of that. It is in seconds. So 1 hour 10, 1 hour 20. Calculate what is the time in seconds. You know that. So like that, we can design the pulse sequence. Pulse durations are important because during this duration, many things happen. Pulse delays are important because during this time we can create coherences. You know what is a coherence? I told you in the first or second class itself. Bring the magnetization from Z axis to XY plane. All spin packets, all the magnetization vectors are immediately, they will at a given time, they will be brought back to coherence in say in one phase. There is a phase coherence is created. Then afterwards, of course, there is a phase decoherence. That is a different question. So for creating coherences, for transferring of coherence, one magnetization can be transferred to other spin, and we can modulate all those things, encode it to a different spin. All those things can be done. So these delays, pulse widths, pulse flip angles, all matter a lot. And phase of the pulse, in which direction you apply, matters a lot. And which direction you apply, in which direction you detect, that matters also a lot. So finally, all these things we take into account for designing a pulse of our choice, experiment of our choice. And the final step is reading out the signal by detecting pulse. It is called read pulse, and then collect the free induction decay. That is the last detection period of the multidimensional experiment. You understood what I am trying to say? So designing of the pulse sequence requires little bit understanding of the spin dynamics, so that we should know what is happening to the magnetization during the application of different pulses of different width and different nuclei with the different delays, how they are evolving. If you understand that, you know what is the final outcome. That is the way we design the pulse sequencer. So in each 2D experiment, relationship between the two or three molecules are established by transfer of magnetization between this. Okay, remember. Okay, so how we do the transfer the magnetization, everything is another type of discussion we have to do. What I will do is, I'll stop at this. In this class, I have told you more about two-dimensional NMR, continued from last two classes, and I discussed about varieties of pulse sequences available. What is pulse sequences? These pulse sequences will give what type of 2D information from the spectrum we can derive in a particular type of 2D experiment. And how do you choose the 2D experiment for you? What should be the size of the molecule for a particular 2D or 3D experiment? And how much utility is there? Everything we have discussed today. We'll come back in the next class and discuss more about these things. And literally we will start analyzing couple of 2D spectra so that we get more familiarity.